So data in the wild. So what is that about? It's basically, again, I showed you this cartoon before, and so now we were at university, basically, or we spent a couple of weeks at university, and that's the woman on the right that has a clue about things and knows about all these concepts. And then there's reality, there's in the wild, how people create web applications and create databases. And that can be quite a difference to how things should be done. And I want to tell you a bit more about that. My motivation of that is, so I was protected in a bubble. I did my at the time was a diploma thesis, and I did my PhD thesis. And immediately after PhD thesis in database technology, I joined a company that was famous for doing database technology. And it couldn't be, it was a shock. I was in shock like for 3 months seeing how they developed stuff and what went wrong. It was really, wow. And this is inspired by that. And since then, I've been seeing that over and over again, things doing in super stupid ways, basic concepts being violated, yeah. And you will see that stuff, yeah. And it's sometimes really hard to comprehend why things are done like that, but I don't know, yeah. But just to give you some ideas on where to be careful and how things might be done differently in the wild. Okay, so basically I always do it like that. In this slide set, so there's this unique concept we learned about, entity relationship modeling, relational model, relational algebra, tra-la-la-la, and then I have a different column in the wild, how it might be done in the wild, and then some note on, okay, a technique that might be useful here to keep in mind when working on this kind of problem. So we learned about that you should be using entity relationship modeling. No matter what you do, first draw an entity relationship diagram. However, what you see in the wild is often there's no modeling whatsoever. No interaction with customers. You prefer to get started straight away. You hack something into the database, create some wild tables without thinking about a real model. Or what you also see is people use other data models like XML, JSON, object-oriented models, graphical models, a graph. No sub-schemas, no logical data independence. I will explain that in a moment what that means. We haven't used that so far. That's a very powerful tool you might use in bigger projects. So people don't follow the design process we learned about in this class. Yeah, same for the relational model. So there are no relations. So in the wild there are tables. They are then iteratively extended over the years. Attributes and tables are continuously added. And you see that very often in companies. Yeah, I need another attribute, I need another column, just add it. And then tables grow and grow over time. So in production systems, you sometimes have thousands of columns in a single table. No one knows what these columns are about. It's impossible to maintain, it's super buggy, it's not robust, it's a disaster. Yeah? Because people just extend the model for minor changes. It actually also leads to what you should have in a project is someone who's responsible for the data model only and makes decisions on the data model, a person who is allowed to change the data model. That not any developer should be allowed to change the data model. It should be few persons that are super clear about what can be added and what can be changed. But typically any developer can change something. Yeah, then of course you see that things are hidden by object relational models and wrappers. We talked about that in Django, yeah, so it's not so clear what's happening in the database sometimes. There are redundancies in these models, you see that very often, so that information can be represented in different ways or is represented in different ways. Yeah? And the clear rule here is always never ever do that. If you're tempted to do that because it's easier at the moment for you, you're doing it wrong. There is no excuse whatsoever for introducing redundancies in a relational model, not a single one. Yeah? Don't do it. If you start doing that, then it's over. Yeah? Never do that. Yeah, no normalization. I mentioned that again in a moment. I think I mentioned it at some point, what normalization is about. There are many legacy fields. So at some point, those fields were used for parts of the application. Maybe now they're not used anymore. Maybe they contain some data. Maybe they don't. No one really knows the dependency. No views, that's also very common. So the dynamic views are not used, or two broadly defined domains. Yeah? So the type of a column is defined in a way that you can store anything in that, rather than restricting it to avoid erroneous data being inserted. And there are a couple of techniques in that space. ORM, we already learned about basically, and Django. Yeah, but the others maybe I mentioned in a moment. Then relational algebra, that's also interesting. There are a couple of, with a wave of data science, a couple of programming libraries appeared, the worst being pandas. It's really the worst library I've seen in that space. However, it's used by many people, but the API is absolutely terrible, and it shows that the people who did that have no clue about relational algebra. It reinvents the wheel, it does things in very bad ways, it expresses it in very bad ways. It's just bad. Yeah? A better example is Spark. I will explain that in a moment, what that means. That's basically, you could say, an implementation of relational algebra in a way that also ships with an optimizer. They're doing it right. Yeah? That's a different thing. Okay, so just as a reminder, I think we had that before. Physical data independence is the idea that the database schema is independent of its physical realization. Changes to the physical representation of the data, be it hardware, indexes, data layouts, whatsoever, have no effect on the database schema. So if you draw it in a layered diagram like that, it means that your logical layer doesn't have to know how the data is represented, how it is stored, which file format are you using, which data structures are you using, and so forth and so forth. So what you define on the schema level is independent from the physical stuff you do with that, to realize the stuff. Yeah? We had this physical data independence in many parts of the lecture. Initially, I stressed that a lot, saying, no, we don't care about how that is done physically. We also had that when talking about operators, logical and physical operators. It's kind of physical data independence in a way, or algorithmic data independence, algorithmic independence if you want. You say, no, I just define declaratively what the operator is supposed to do, but I don't say how it is done. The how part comes in with a physical operator, with a concrete algorithm doing that stuff. So and that's a super fundamental concept of databases. It has the advantage that the physical layer can be changed subsequently. Whatever you define in your schema, you don't have to know anything about the physical machine underneath, be it a punch card machine, an analog computer, a modern ARM processor, or quantum processor. It doesn't matter. The schema definition is always the same. Maybe with quantum processors, schemas might be more quantum style. I don't know, but in theory, whatever the computing device, you don't have to know about that. So there's an effort for abstraction, of course. Yeah? You can't think along the lines of data structures and files and data layouts and stuff. Yeah? You have to make these abstractions we learned about. And then there's a second type of independence in databases that's called logical data independence. That's a layer on top saying the views of the end users are independent of the database schema. So now we are one layer above. Before we were here, yeah. Now we are here, and saying, okay, there is a logical layer. Basically, that is a schema we defined with create table. All the create tables we did basically in our schema. But then you say, okay, now I hide this schema under a couple of views. Yeah, I make different views and I write my applications against those views only. So I say the applications are not allowed to access the database schema here. I forbid access to that database schema. I just allow access through so-called subschemas, and those are the subschemas here. And that allows me, for instance, to have a bigger schema, which where I would say, okay, now I define a view where certain applications are only allowed to access some of the tables. Yeah? Imagine, for instance, maybe again a university application that does all kinds of things. One is whatever entering grades, and the other is listing grades, the other is listing lectures and stuff like that. Yeah? So you have tables that list information about your grades and the tables that list information about lectures. So you could have an application that just shows the lectures in the current semester. That application could just have access to the tables that are required, yeah, with the lecture information, but not the grading information of students, of course. Yeah? So by providing a view for each application, you could say, okay, that is a the lecture catalog, where you say, okay, this has only access to the tables with regards to lectures, but not the exam stuff. And that's called logical data independence. That's rarely done, but it might be a useful tool in these situations. Yeah? So for web applications that run on a database that's not shared with other applications, logical data independence is typically not implemented. So that means so till here the sentence means, basically you have one application in mind, and you have your web application stack and a database underneath, and the database only serves this single application. Yeah, but there might be scenarios where this one database serves multiple applications. Yeah, and then you might protect the database, the tables with logical data independence. Yeah, so that's the second part. However, if you're developing a web application that shares data with another app, you may want to consider implementing logical data independence on the database layer. Yeah. So this concept is a bit tricky. Also, if you try to do that, you will see, I mean, how to integrate it in Django. It's possible. Django can work with views. Sometimes these views have the issue that you can't do updates through those views. But if the view is written against a single table, you can. Yeah? So there are things around that you can do that. Yeah? If you want to really be sure that you don't get access to the wrong table, that's a concept you may want to think about. Yeah, then normalization. I mentioned that briefly. So in some database classes in Germany, it's still quite a topic. We had that in previous iterations of this class as well. It's database theory, reasoning about the redundancy you have in your schemas. Yeah, so you have an existing table, and then there's a theory that's called normalization theory, telling you, yeah, you're doing it wrong. It's basically giving us a grade. Yeah, you get a 4. You get a 2. This table gets a 2, and that gets a 1. It's basically grading the quality of those tables. And it's a bit outdated because modern SQL is now on a different planet. So when normalization theory was conceived, yeah, I don't know, I think it was 70s, 80s. It was super early, 40 years or longer ago. Yeah, people were thinking about a strict relational model with atomic values and stuff like that. And as I mentioned before, this is not where we are with SQL 99. So in any data value, any column can be of a set-based type. Yes, you can put in any data value, you can put a table actually. Yeah, so you can say I have tuples, and you have columns, and one column is of type table. That's cool. You can do that. You can do nested tables, yeah, and that's violating all this theory from the get-go. So it's a bit outdated. Yes, it is too much oriented towards atomic domains as of SQL 92. Now we're 2024, 30 years later, so I don't think it doesn't make too much sense. There's one exception though. It's a good tool to reverse engineer an existing messed up database schema. If you ever need to do that, I'm feeling for you that you have to do that. That's quite some difficult work. In particular, keep in mind, if you have an existing database schema and an existing application, the application will access the old database schema. You can't simply redesign the schema without redesigning all the accesses of the application. Yeah, forget it. Yeah, so this makes sense if you say, okay, I kind of keep the schema, but I also redo the application. I did that once a couple of years ago. I took an existing schema and then got it right. Yeah, but I also rewrote the application. So yeah, that's a case where it might make sense. Yeah, and this is about this hard-coded versus Spark. That's a big confusion you also see with developers. And we touched that briefly when we talked about rule-based optimization in this lecture. So basically what you see here is how Spark like our relational algebra would do that. So basically you have kind of operators. You have like here, how do we do that? Maybe let's just look at the graph. That's the easier way. Yeah, so basically you have a graph, again, bottom up, directors, director genres, cross product, there's a selection, and there's a projection. Okay, so you can read that in that order. You can read that as a procedural program. You could read that as, okay, I take directors, I take director genres, I perform a cross product. Whatever the result, I feed that into the selection. Whatever the result, I feed that into that selection. Whatever the result, I feed that into the projection. That's fine. That's a procedural way of reading such a plan. But the other is to read it as a declaration, to say, okay, that is how my result should look like. Yeah? And that's what we learned about in rule-based optimization, saying, that's how you declared what you want to have as your result, but that does not imply that it has to be executed in that order. And that's basically what you exploit in rule-based optimization. You say, I can push these selections down, for instance. We had these rules. So, for instance, to rewrite that to a join, that could be a join operator. Last name is Tarantino, will be pushed here. Genre is mystery, will be pushed here, and so forth. So we rewrite the plan, basically. Yeah? So there's these two ways of reading a plan, and there you have to be really careful in discussions, because from what I'm learning, I also saw that with PhD students, they say, no, it's in that order. It doesn't have to be like that. In particular, if you deal with Spark, if you write a plan like that in Spark, declare it like that, it feels like you're writing a procedural program, but Spark will do anything with that. We'll just say, whatever, I optimize it. I don't care about what you wrote. I will give you something that returns exactly the same result. So everything is fine. Huh? Yeah, and that's something you have to keep in mind. And I call that the two interpretations. Yeah? So this is the procedural interpretation of relational algebra style code, or that's the declarative interpretation. Yeah? No matter whether you look at code or at the tree, you can always both interpret it in both ways. Yeah. Okay, then let's look at a couple of other things we dealt with in this lecture. SQL, of course. In the wild, it's mostly SQL 92, and that only partially. Application logic is often used to read relations into the application and then even do filtering or operations that should have been done by the database in the first place. So SQL is, in some scenarios, just used as a better file system. That's actually how SAP phrased it a couple of years ago. They used databases like that to just access the data and do all the heavy processing in the application. That is not how you should do it, because it doesn't scale. The application will not scale as well as the database is able to scale. The database has all that magic of query optimization. You don't want to reinvent that. Yeah? So the rule is try to push down as much as possible of the computation down to the database. Yeah? And that means don't just use SQL as a tuple access file system. You also see materialized views. I warned you of that. Don't use that stuff. User logic, horror story. User logic, horror story. That's the one. Yeah, I think that there was a story. Did I mention that? I don't know. There was a horror story a couple of years ago where the manager decided, we need to get rid of our database system from the 60s finally and get one of these relational database systems. And they decided to put in charge one of their most senior architects and who made the migration to relational systems actually. And then eventually they found out it didn't help. The scaling problems were not solved at all. It was slow as hell. It didn't work. Yeah? And then they put a consultant on that, and the consultant looked at it. So basically, what the guy did was, previously they were working on files. So what did he do? For each file, he would create a tuple in the relational database system where you put the contents of the file in a blob. Yeah, so basically, rather than having a separate file in a file system, you would now have a file in the relation. Each tuple would represent a file. And then you would rewrite the logic against that. And I mean, you're not using any features of the database system if you do stuff like that. Yeah, you have to break it into smaller parts. Otherwise, I still have a link to that somewhere. I think it was in earlier slides. Okay, then data economy. So the idea to only store the data that is required for the application. Don't store stuff you never use anyway, be really economical in the attributes you store, the user information you store, while the opposite is the case. Yeah? Companies try to store as much data as possible and sell it. We just had in the news, there was just reports on profile information, on geographic location data being sold. Yeah, so that's a big problem in our society. Yeah, then asset, atomicity, I mentioned that before, that's often not used to protect multiple tuples, changes on multiple tuples, but in the style that you do in atomicity on a change of a single tuple. That's basically what you find in the so-called NoSQL domain or key value store semantics. I have a slide on that in a moment. But that's not what a real transaction is about. From the database perspective, yeah, you may be modifying as many tuples as you want and still make those changes atomic. That's the idea, not just per single tuple. Yeah, then consistency is a big topic. So you have an idea about your data, you know it should be consistent. We have the banking example. You do a transfer within the bank before the transfer and after. It should be the same sum of all accounts. That's a consistency constraint. And you can have many of those. And you can check them automatically. And there's a huge array of tools to do that. It's completely crazy what databases offer. Do you want to use that? I'm not so sure. So some of these tools are rather old, but super powerful. One is triggers. I will explain that in a moment. And Postgres has a second similar system, a rule-based system. I also mentioned that in a moment, just for you to know, because it might be interesting in some situations, because you can then do checks on the data in your schema in the database. Yeah, it's an additional constraint you can implement in the database directly rather than doing it on the application layer. It's actually a pretty cool concept, just a bit more advanced. Yeah, then the isolation, so concurrency control, they're all possible relaxations with or without knowledge of the consequences. Also affects atomicity. There's a concept like eventual consistency I would like to mention briefly in one of the following slides. But there are many more. And durability, yeah, I don't know. Well, okay, there's some backup strategy. Well, what does durability really mean? Am I really durable in the sense that if a transaction commits that I already archived the data, and so forth and so forth. Yeah, so, okay. Yeah, that's basically related. So now let's go through that. So whenever I have a note here, I basically have some new slides on that in the following. And that's a simple exercise you can do. So example, you have a user who wants to see part of your data. Yeah, so maybe it's a table with a couple of thousand entries, and now the user wants to filter that table. And then you can make a decision on where to filter the data. Yeah, so you can where do you execute the data? Yeah? So the one extreme is the user reads the entire table and filters the tuples in his or her head. Yeah, you read 1,000 tuples. Oh yeah, that's interesting. No, that's not interesting. That's interesting. No, that's not interesting. That's yeah, the latest point in time where you can filter the data. The other is you do it in the front end. Yeah, the front end could do the filtering. You send all the table up to the front end. We actually did that in one of our applications, and we were surprised how quickly that breaks. In particular, if you send data around with JSON. Yeah, we had to change that. We were hoping for coding that we could keep that longer. It didn't work. So we sent the table, sent all the data from the database system up to the front end, and then do the filtering in your JavaScript code. That's another option. Okay. Or you could send up the entire table to the application server. So basically in the application server, be it ORM, you do a model.objects.all or something like that and loop over that, and then, yeah, if first name equals tra-la-la-la-la, make it part of the result. You execute a filter on the application server. Yeah. You could also do that there. Or you do it in the database system through a where clause. That's another option. Yes, and basically the database system will read the file into main memory or whatnot, however that's organized in the database system, yeah, or maybe it has an index, I don't know, and then it selects the qualifying tuples. Or the operating system is smart enough to pre-filter. Maybe the operating system can be tweaked in a way that it doesn't deliver all files to the database system, but just the ones having qualifying information. Yeah? So just certain files that the operating system is sure contain the data are delivered up to the database system. So the operating system does part of the filtering. Or you do it in hardware. You have hardware that is able to filter it. I don't mean that the CPU is running a program, yeah, eventually. I mean, all of these things are running programs on the CPU. I really mean that is built in silicon, that the hardware can filter out data. Yeah? And there are many approaches to that. Important to know is what's called smart disks that exists for SSDs, but also for hard disks. So those are storage devices that can take a filter condition and then only deliver the data up that qualify under a certain predicate. Yeah, so that's possible. It's called smart disks, rarely used, but for high performance systems, it makes a lot of sense. Even exists for the DRAM, and you filter directly in the RAM, pre-filter in the RAM, and only send certain subsets of the data to the CPU. Why would that be a good idea? And what are the trade-offs here anyway? When should you do what? So you have all these options. And I would claim there are use cases for each and every one. Any idea? I mean, if you're a full-stack web developer, eventually you will have to implement something like a filter. I mean, we had one of the projects did a filter, right? How do you filter out data? What could be a drawback? What could be an advantage of doing it in a specific layer? No idea? What if I do it in the front end? What could be the drawback? I send all the data up to the front end and only filter in the front end. What could be a drawback of that approach? Yeah?
Maybe it would be too much of excessive processing on the front end.
Yeah, true. Right, exactly. He's saying it's too much excessive processing on the front end, also factoring in that front is probably some JavaScript, maybe not that efficient as some C++ stuff or whatever you use in the back end in the binary. True. There's a second aspect here. Yeah?
I think it could also be useful to do it in the front end, depending on how you use the data in the front end.
Uh-huh.
In the larger process, you will use all of the data in different filter settings.
Mm-hmm.
Maybe sensible to cache the data at least in the front end.
Very good. Yeah? So he's saying, okay, if you load the data anyway in the front end, you're using it at some point or the other, I can load it anyway and do the filtering, who cares? Very good. Yeah? But there's another drawback, yeah? Yeah, could be. In general, you should that should be avoided already when pulling the data. You should, for access control, of course. Yeah, the access control must not happen in the UI. It must happen already in Django or the DAF or whatever the server is. Yeah, as early as possible. Yeah? Yeah, but there's another concern you have here when you pull a lot of data in the UI. Does anyone see that? Yeah. Right, exactly. The network cost for sending data. You look at the internet here on campus. It's a good example. You draw like a billion records to your UI. Maybe that's not going to fly. You have to wait a lot of time. Yeah. So this is an application of what we called in query optimization predicate pushdown. We push down the filter as much as possible to avoid networking cost. And network cost happens on multiple levels here. We have different types of networks, so to say. There's a network sending stuff over HTTP from the application server to the front and the standard network, the internet. But there's also a transfer cost from the database system to the application server. There's transfer cost from operating system to database system, and even from hardware. There's a bus system sending data to the operating system. And this bus system, even though it might be very capable and has a high bandwidth, it might become the bottleneck in high-performance applications. So what you want to do is you always want to avoid having to send around a lot of stuff over between the different layers. Yeah? So you want to filter as early as possible. And that means the best trade-off in the 95% case is to filter it on the database system. Yeah? For some high-performance systems, you go a little deeper. You might consider buying smart disks, but it's really super high-performance systems. Yeah? But the standard approach should always be think about where to filter, and if in doubt, filter on the database system. Yeah? And that holds for all operations where you can filter out information. So where to implement which functionality, that's what we learned about. And this is important maybe to wrap this up. It could be a problem if you want to scale an application, if you want to scale it up. If you have too much code that does heavy lifting, does heavy data processing in the application layer, you might run into problems scaling the application. So an application is much easier to scale if stuff was delegated as much as possible down to the database system. Yeah, and that's really an important rule here. So where are we? We're on this table. We looked at SQL, how SQL could be used for individual tuple access or for bigger things. And now we look at a couple of other things here. And the first will be key value semantics. You will also see that in the wild being used, so-called key value stores in the context of NoSQL systems. So what's a key value store? That allows for the efficient storage and retrieval of keys mapped to arbitrary values. Transactions over multiple keys are typically not supported. Functionality and queries that cannot be mapped to key value semantics are usually insufficiently supported. So basically, a key value store could be used for something like that. Basically, you're using it every day. If you type in a URL that maps to the content of a web page, actually kind of, if you factor out the JavaScript stuff that might be loading other things, yeah, but if the URL really maps to an HTML page without JavaScript, that's a key value store in a way. The internet is a key value store. Same holds for the file system. Any hierarchical file path, yeah, with directories of /a/b/c, to-do.txt. Yeah, so this hierarchical file path plus the file name is a key, and that maps to the content of the file, be it a text or binary file. So your file system is a key value store. That easy. Or you have an ID that maps to a JSON document. That's done in some systems that map keys to documents, or in particular JSON documents. That's all what a key value store is doing. So you have very efficient and sufficient, so they're very efficient, and they are sufficient if no other access patterns are needed. If the only thing you want to do is look up by a key you're happy with, like in the file system, like in the URL case, yeah, then it's okay. Yeah? And what's strong about these products is what's called scale out. Yeah? So there are key value stores out there. Basically, this entire hype about key value stores was triggered by large internet companies that had to scale their applications over the globe. Yeah? And they had a highly distributed system, and they had to make these key value stores work over the globe. And so there are a couple of free products out there that can do that, that allow you to easily scale this stuff to arbitrary amounts of data. If you need that, not sure. Yeah. So because the use case is very limited, so it's just the key access. If you want to access data by any other attribute, some of these products allow for secondary indexes to build, but it's not so, you can't compete with a relational database system. And if you think about that, this is nothing but a distributed index, a hash map, what these systems support. You can mimic it basically in every relational system. Yeah, oops. You just make one table. That's your table R. You make two attributes, a key and a value. Yeah, that's your key. That's your schema. And then, of course, here for this column, the database should use an index, B-tree, hash table, whatever. Yeah, this is your key value store. End of the story. Yeah, it's really the only advantage is scalability, really, of key value stores. So, and if you use a key value store on your stack, you might be tempted to using different storage systems. And we had that in one of the slide sets. Whenever you use different database products, you have the difficulty of, okay, some part of the data is stored in that database system, the other in that database system. What if I have a query that spans both? Tra-la-la-la-la-la. That's not going to work. Just introduces unnecessary complications. Yeah, then the other thing with respect to consistency, the C in ACID, triggers and rules, it's the same idea. And so-called ECA rules, event condition action rules, basically looks like this. So you specify an event, and then you say, okay, you specify a condition. It's the second thing, a condition that is checked for that specific event. You can actually fuse the first two if you want. And then you execute an action. Yeah? So basically, if a certain rule triggers, if a specific condition is true, then you perform a certain action. And many database products ship with what's called database triggers. So you can basically implement these kind of rules inside the database system already through SQL style language in a way. For instance, here's an example how you could do that. You create a trigger called log update, and that's saying after an update on the accounts table for each row, when the old row, basically here we have placeholders for the old state of the table and the new state of the table. So basically you can check for each row whether the old attribute values are distinct from the new attribute values. Then you call that specific function that logs account updates, for instance. Yeah? So that's another, these are called, you can basically register arbitrary functions in many database systems. Sometimes they're implemented with procedural SQL, sometimes you can implement them with other programming languages. Yeah? But basically, the first part is the trigger part saying, okay, on certain conditions, on certain events, you can do something. And that's basically the action being executed then. Yeah? And again, for consistency purposes, it's a good idea. I also did a video on that. We had that in some previous lecture. If you're interested, I think it's a couple of videos on how to do that in Postgres. So it's a powerful tool. So if you're interested, take a look at the video or at the Postgres documentation. It's suitable for complex consistency conditions, tracing, event-based changing of relations, and these events should be implemented in the database system, not in the application, where they belong. However, there are a couple of problems here, so it's not so easy to use. So, I remember when I first prepared that for the lecture a while ago with Postgres, it was not that you could directly use it. There were really some pitfalls you had to be aware of. Once you knew about that, everything was fine. No? What's even more problematic is debugging this stuff. No? So now what happens is you change a table and you feel like, okay, I insert, update, delete, whatever, but then some trigger kicks in. Yeah, maybe that does something, changing another table, which again has a trigger, triggering again. Yes, you might fire a cascade of triggers just by doing one tuple insert, and that's performance-wise also a bit hard to keep under control. So I would be careful. I would be here and there. You use it if really you feel like, yeah, that's much better to do it, but you can really mess up your database with that as well. That's in infinite loops, yeah, you can trigger, you insert something here, which triggers something there, which triggers something to insert, boom, 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 yeah. But now you know about that. Okay, a couple of other things we touched. Security, huge topic, often designed or hacked in afterwards. Privacy, conceived or hacked in afterwards, if it's considered as an issue at all. Of course, you must consider it from the get-go. Quality assurance in a project, no staging environment, no unit or UI tests, no CI. So that's basically all the software engineering things you should do. There are also many social things that can go wrong in these projects, of course. Automatic testing, there's application testing versus consistency as of triggers. Documentation might be an issue, meaningless names of tables and attributes, semantics unclear, user roles unclear, or access controls not defined. Maybe anyone has access to all, everybody has access to all tables in the database system, probably not a good idea. Effects across tables unclear, and so forth and so forth. So it's basically also what you see when you don't use information hiding. It's the same effects you're seeing here. Again, you could use logical data independence as shown above, or use mere access control, for instance. Extensibility, difficult to impossible due to missing interfaces and views. So if you have spaghetti code in your databases or a spaghetti schema, same problems as with spaghetti code. Dependencies might be unknown, so maybe you better don't touch the stuff. Maybe you don't refactor because you don't know who's using it, and so forth and so forth. Of course, now with modern tools that gets much easier, but it's still a challenge. So sometimes you don't want to change the running system, don't touch it, it's working, you might get in trouble. So people tend to not refactor and just add stuff. Then physical design. In the wild, how do you do that? Buy a new hardware, buy a new database system, indexes. There are a couple of mistakes you can do. Basically what you have to keep in mind, yes, there's physical data independence. Yes, you don't have to care about how the data is organized. You define your schema and you're good to go. In practice, someone has to define the mapping. Someone has to say, okay, how do I map my schema to a machine, to indexes, to structures? And that's done by a database administrator. And he has a lot of power to influence the performance of the system. It's a long topic, and there are tools that can help you with that. Modern database systems have semi-automatic tools called physical design advisory that can suggest indexes, for instance. They say, oh yeah, I mean, with the kind of queries you are sending, that index would be a good idea, or that would be a good idea. That index is a bad idea. Or maybe you partition the data, or maybe you need another hard disk, stuff like that. Another hard disk, another SSD or whatever. So performance tuning can be supported by these systems. Okay, but I can't explain all of that, just some. I hope you saw that in some software engineering lecture. But that's really something you must have when developing a system. Other than, okay, CI and CD, of course, and Git, sure. But there are different environments you should be using when developing a system, and some projects don't do that. So this could be something like that, could be simpler, could even be more involved. But basically, you have a development system where you develop new features on any sample data. You can play with that, you can crash it and ruin it, it's fine. Basically, whatever you do in your feature branch locally and on your laptop, typically, you could also do it on a server, but that's something, if you break that, it doesn't matter. Then there's typically a test system that could be part of CI, or it could be an independent system where you're testing new features, typically connected through continuous integration. You could actually also run that as a replica. So what we do in our project is we have a replica of the production system, which is super useful because then you can work with real data but don't ruin anything. Then staging is basically the last system before production to test new features. So that should correspond exactly to your production system. And that's basically, okay, that's to correct me. So test is typically on fake data and staging is on the real data. That's also how we do it. But that's the last control, so to say, the last quality control. Afterwards comes production. So you should ideally run that as a replica of a production system. So then you can play with production data and see whether your feature that you already believed works. Yeah? So basically, if the test system maybe on some fake data, like used in our BDE project, says, yeah, it's fine, or the test pass looks good, yeah, then you haven't seen production data. Yeah? So you can think as much as you want about user scenarios and fake data as you want. You will be missing cases. Yeah? I've learned that the hard way in the past months. Really, yeah? we deployed our system in January. We thought about that so much. We had so crazy cases of data you would only see with production data. Yeah? So staging is basically where you have a feature and feel like, hey, maybe I checked, maybe that's something might be really depending on production data where you can play with that. Yeah? And then if you see, oh, there's an error, then you can fix that and run the tests again. Yeah? And production, or for short prod, is the production system with real data and real customers, of course. Yeah? Yeah, and I mentioned that when we talked about trading, banking, and ticket systems. So one reason for this failure of the banking systems and one of the banks was that they did an important change in production rather than in staging. They changed production data in a way that completely ruined the database, and chaos broke loose. Yeah, this physical design advisory and performance tuning. Yeah, there are a couple of tools. Problem is, it's our auto-tune was now stopped, right? People have worked on that for 30 years or something. Typically, you only get that with more expensive database systems, like SQL Server, for instance. It's a good advisory tool. It's really more for bigger companies, for smaller database systems and small applications, yeah, I don't know. Yeah, but then maybe you don't even need that stuff. Yeah? But for big database systems, you will want to look at that. There was a project that was stopped recently by a colleague from CMU, basically doing ML and AI to configure, to come up with a physical design. It was very successful. I think they had some legal issue with the startup, and therefore they had to stop it. Okay, what else do I have? Yeah, data management in the wild is often aligned with the organizational hierarchy. So you look at the organizational chart of a company, then you also see how the IT is organized often. There are social aspects, especially power games. Yeah, so that's very annoying. So if you want to work on an IT problem or a cool technical problem, and then you're drawn into some political discussions, which is you have to want that. You want to. I don't want to do these kind of things. Yeah? Data might be distributed across different systems and databases. Query processing might happen along organizational hierarchies, which is not the technically best solution. There might be many data integration problems. Data integration problems, that's also a big gap you will be seeing. So in the lecture, we always like, oh, there's one database. Yeah, and then it's one application. Or there's one database and there's several applications. Yeah, enter a company and then you see, oh, there are dozens of databases. Some of them are connected, some of them replicate the data, some of them are integrated, talk to each other, others don't. Everything is possible. And that triggers a lot of work. Yeah? The more databases you have, the more integration effort, the more errors you get, and that might be quite a mess. Yeah. Another very important thing I've seen so many times is so the question of knowledge of the people working in a project. So the perceived knowledge or the active concealment or ignoring of one's own lack of knowledge. So what I mean by that is, that was a database example I just mentioned. That's the link to this put one document in a tuple. Maybe you should read that back home. That's really cool. Yeah, the fact that there are many people out there that do these kind of projects but don't have a clue. I've seen that so many times, and it's really terrible if you think about that. I mean, that's right. It's not only in computer science. You also see that in other fields. People do jobs who shouldn't be doing these jobs. But in IT, it can be a disaster. A really, really big disaster, and with sensitive data. Then concepts. So people confuse concepts with specific implementations and tools. I will have a couple of slides on that in a moment here. We'll show that soon, what I mean about that. And then this buzzword stuff, I will also I showed that slide before here, I'm not sure, but I will show it again here. So basically what I mean by that is in these projects, you often have ambiguous communication. And you also, I see that also in other fields, but it's really, really insane in IT. In all of IT, you see that. And basically, it's something like that. So you have one person saying, there's big data. And yeah, big data is a term that's very loosely defined, or in other words, has multiple interpretations or meanings. So when someone says big data, or if I write it on the slide, or if I write it on the blackboard, yeah, or just say it, it's not necessarily clear what I mean by that. Do I mean it's kind of a large data set? Whatever large means. Is it terabytes, petabyte, exabyte? I don't know. What is large anyway? There's a famous definition that's called the 4 V's: volume, veracity, variety, and some other V, I forgot. Others might be influenced, okay, big data, that's about mass surveillance, NSA stuff, right? Others might, big data, that's Spark, right? Or 10 years ago, people thought, big data, that's MapReduce. That was a popular framework introduced by Google, and so forth and so forth. So it's not clear what's meant by that. And that's the problem, because now if someone hears it, he might have a different interpretation. Yeah? So if he hears big data, he actually hears, MapReduce. Yeah, that's what he's talking about. Yeah? Whereas in fact, the person on the left might, no, by big data, this person means large data, and the other person means MapReduce. So yeah, they believe they're talking about the same thing, big data in a way, whereas one is talking about large data and the other is talking about MapReduce. Yeah? Hence, you have a translation error. So you translated large data from the brain of the person on the left to MapReduce by the person on the right. Yeah? And that's a problem. And you see that in many discussions in IT. It's a huge problem. In clear communication, in contrast, you should use terms that are clearly defined. So like relational algebra, for instance, that basically maps through these symbols, these Greek symbols, join operators, stuff like that. There's not much room for interpretation. And that means if someone hears relational algebra and learned about relational algebra, at least there's no translation error. Relational algebra was translated from one brain to relational algebra in the other brain. There's no error whatsoever. Yeah, and that leads to what I call the buzzword bullshit bingo landscape. Basically, on the x-axis, I depict the number of meanings for the different terms. The y-axis doesn't mean anything here. There's no y-axis here, okay? It's just to be able to show it. So the x-axis here is the important thing. And basically, all of these concepts, all of these terms are non-ambiguous. If we say relational algebra, it's clear. If it's predicate pushdown, it's clear. Relational model, clear. Data layout, yeah, maybe from what you know so far. Not so clear. If you pass the core lecture, you know what I mean. Cost-based optimization should be clear. We talked about that, what that means. So those are non-ambiguous terms. And the further you go to the right, yeah, the more ambiguous and the more buzzwordy these terms become. Yeah, so big data, what the heck does that mean? I have no idea, says professor of big data engineering. Yeah? AI, NoSQL, blockchain, what the heck? Machine learning, super overloaded with different terms, and so forth and so forth. Yeah? So that is why my clear recommendation for you is, if you are in a technical discussion, only use terms on the left. Very important, non-ambiguous. If you want to have venture capital or get a job, or become a manager, only use these terms. Yeah? Works, still works super great. Huh? I mean, again, I say that every time I do this lecture. At some point, my chair was named Information Systems. That's the official term of my group. Yeah, so I renamed it to Big Data Analytics Group. Yeah, and since then, I've been receiving many more calls with offers for projects and consulting and stuff. It's marketing term. It works. Yeah. Yeah, I do the same thing as before, basically, right? But yeah. Okay, and another thing is concept versus technology. I've seen that so many times. It's so terrible. Also for people who have a degree in computer science. Guys, what are you doing? And that's a problem. Confusing dimensions. And there are 3 dimensions. And one is this buzzword dimension we talked about. Yeah? It's clear, fancy sounding buzzwords, yeah, super duper, whatever that means, marketing. But then there's technical principles and patterns. That is what you learn about in lectures. That is what the computer science program is about. You learn about concepts. It's not about there's a library XYZ and you learn exactly how to use the library. Yeah, we do that a little bit as a side effect. That's fine. Yeah? But at the end of the day, it's about these concepts. Yeah? What are these things about in principle? Predicate, pushdown is like an inherent principle of nature, if you wish. Yeah? Like whatever Newton's law of gravity or something like that. That's on the same level. It's so fundamental, you see it everywhere. Yeah? And all of these are super principle concepts. Yeah? But this is often confused with, before I go that, basically, yeah, so we had that before in this lecture. So predicate pushdown, just meaning filter and project data as early as possible. And there's so many variants and shades of this predicate pushdown. It's really crazy. Could write a book on that. Huh? But then also for the relational model, yes, you have the idea that you model all data as multi-attribute sets. And that gets confused very quickly with concrete implementations. Yeah? For instance, tables. Data frames in the data science pandas world, column stores, row stores, those are terms on a different level, and that leads to dimension 3, concrete software platforms, concrete implementations and frameworks. Yeah? So that's, maybe I can jump over that, and that's basically a dimension where you make a decision on a realization. You say, okay, I will be using Spark, I will be using Postgres, I will be using MongoDB, or some Python library XYZ. Those are concrete realizations, but that's not about the concepts. Now, the interesting thing is to understand the concepts. And then if you solve the problem on the conceptual level, then you map it to this dimension 3. Then you make a decision on the software platform. Yeah? If you want to do a web application, you have a principled architecture into layers. You don't have to say, okay, okay, Professor Dittrich said I must be using Django and the relational database system and Vue.js. No, those are just examples from dimension 3. You can use whatever you want. The principles will stay the same. Yeah, it's important to solve concepts on the conceptual level as long as possible and really postpone the decision to jump to dimension 3, because once you jump into that, of course, you're binding to sell yourself to a certain technology. Yeah? And that's basically, what that means is, okay, buzzwords, forget about that, it's about marketing, but when you solve a problem, you should always solve it on this level. That's what one of the most important things to learn in your study program. You always solve stuff on this conceptual level, and only as an afterthought. Okay, it depends on how long you can stay on this level. I understand, yeah, but you must not solve a problem by saying, okay, that's easy. I will be using Spark for that, and then I put it into a key value store and do a nice React interface on top of that. That's IT developer gibberish, but that's not what you should take away from a study program, yeah? Because if you stay here, yeah, you solve the real problem. You still have all the freedom to make a decision on a specific software platform. If you jump too early into a software platform, you're bound to it. And maybe you might be overlooking the conceptual solutions to your problem. Yeah? So that's really super, super important to stay here as long as possible. Yeah? I'm not saying only stay here, yeah? But you somehow have to find also the right moment to step to dimension 3. Yeah? But I'm saying don't start with dimension 3. That's wrong. Okay, and this is a horror story I saw 2 years ago. Basically, the problem was a large web application. I'm not going to say which one, which small country, and which university. There was a large web application with terribly slow performance. Yeah? So basically, users would try to use the web application, and there was no reaction. It was taking minutes or an hour for a reaction. And that was a performance number where you could do the math that's, okay, we are a factor 10,000 slower than it should be. Yeah, and I think I did the computation at the math. Assume the ICE is not running at 200 kilometers an hour, but so that's 200,000 meters per hour, but rather 20 meters per hour. That would be the relationship in real world. 20 meters per hour performance from an ICE train. It was an SAP system with approximately 100,000 tables. That's kind of standard in these SAP systems of tens of thousands of tables. And they don't have names you understand directly. They have names like R45, F7, tra-la-la-la-la. What the heck? Yeah? Apparently no or hardly any views. And completely ridiculous performance numbers. Really doesn't make any sense. And I got curious because I felt like, okay, I'm a creative person. I can imagine things. That's my job. But I cannot imagine how you can bring down a system by a factor 10,000. I want to find out why. Yeah? So I talked to these people and I offered consulting. It finally didn't materialize. We had 1 or 2 interactions. But basically, here's a couple of things if you ever are in a scenario what you should do if you are there. So you should profile the runtime of the application versus the runtime of the database query. If you think along the lines of the layers I showed you multiple times, you need to find out where the heck is the performance problem, on which layer is it happening. Is it the UI, is the application server, is the database system? The first thing you need to find out, isolate the problem. Yeah? So you can profile the runtime of the database query on the system with and without load. That's a pretty standard question. So is the server overloaded? Or even if the server is not overloaded, it's that slow. That's maybe you want to make sure what you're talking about. So you can profile the database performance on an underutilized system. And it might actually be the case that just this query is so slow for whatever reason that it brings down the entire stack. Huh? You can think about physical design, including indexes and partitioning and stuff to fix these things. So. Yeah, there were more than 30,000 users. So if in this situation, maybe you want to look at the load distribution, yeah, after you root out the other things I showed on the previous slide, yeah, which part of the system receives which load. You can play tricks like see if the application server, so Django, and the database server are on the same server. You should find out, is it the application server, the database server? Do you want to split them on different machines? Common trick being played. That's what you can do. You should have clear performance monitoring. Yes, so I didn't see any of that in that project. So you shouldn't wait for users to come and say, hey, the application is slow. You should have alerts. You should have checks for, okay, how fast is my system? How fast is this component of my system? And if the system becomes slower, there should be alerts for that. There are so many tools that allow you to do that. What you could also do in such a scenario is maybe that's the cheapest typically is to look at the storage system. Yeah, if the storage system is based on hard disk, get rid of it. Use SSDs. We're actually currently doing that at our department as well. It's an easy fix, gives you so and so much more performance. You can do performance load tests. Actually, if you think about unit tests that tests the functionality of whatever component of your system, or even end-to-end tests in the sense of Playwright, you could also have performance tests as part of your CI. Why not? Yeah, you could try to understand whether all the functionality you want to provide is still within a certain range, still fulfills a certain SLA or not. Yeah? Could be part of your CI, yeah? because it may happen that you introduce some functionality where the unit test still passes for a function, yeah, but the function becomes so much slower that it affects performance of your system. Yeah? So performance tests could be part of your CI. Yeah, there were social interactions, like project setup was like 3 companies or three entities involved in the development, each with several managers, project leaders, sub-project leaders, developers with very different database knowledge. So everything from very good, there was one guy who was really proficient in databases, to individual managers, studied completely different things. None of them was a computer scientist. Project leaders, application developers with little to zero knowledge, mostly non-computer scientists. And they were all finger pointing. Yeah? So rather than, okay, Houston, we have a problem, let's try to find out what the heck the problem is, they were just pointing fingers at each other, saying, no, it's your part of the application. No, it must be you, we're sure. But there was no proof to demonstrate that they were sure. It was terrible. Huh? Yeah, and the solution space here is actually trivial in a way. You should profile the queries, as said before, find out where the performance bottleneck is, isolate components of the system, try to find that out, and then you know, okay, it's that part of the system. Yeah. Here it was probably several performance problems combined. Again, we just had 1 or 2 meetings, and I didn't follow up on that. One part of that is also identify and address deficits in the staff, either train people appropriately or fire them. And that's how I mean it. I mean it like that. Phrasing it differently, an IT project hinges so much on the qualification of the people. It's insane. Yeah? And you don't want to have people that are not qualified for the project. They should be working on other projects where they match better with their qualifications. But I see many projects where the people have shiny titles. Oh, I did this tra-la-la-la, SAP qualification, whatnot. But they didn't really study computer science, for instance. Yeah? They don't really have experience in a specific area, and that's a nightmare. That's the best way to ruin your project. So for these projects, it's like building for IT, it seems to be okay. Okay. Don't get emotional, Jens. Breathing in and out, breathing in and out, breathing. Okay. Yeah, imagine you want to build a turbine for a jet plane. A jet plane has these turbines. Yeah. Would you get the idea that you get someone who learned to become a baker, put them in a 3 months lifelong learning course, and then say, okay, it's more or less the same. Now you can build this jet turbine. No, it's obvious that that's not going to work, but that happens all the time in IT, and that's absolutely terrible. So in summary, so often you see in the wild there's a lack of fit between training and task, and when you pass this lecture, you're already so much beyond and know a lot about databases, you should be good to go. But that's not the standard. So database technology is often used by people who have no real clue, aggravated by the fact that these people often believe they have a clue. In addition, these people are often also resistant to advice. It's another thing. Yeah? You come into a project, you see this is obviously wrong, and hey, why not use this and that? And did you hear about it? No, we have always been doing it like that, it's okay. Yeah? And that leads to an unpleasant mixture. This unpleasant mixture leads to a variety of performance problems, security issues, architectural mistakes, including purchasing decisions. Yeah? Companies buy database products they shouldn't buy because they don't even need this stuff. Yeah? And also enormously high costs in the end. And again, would you have your teeth treated by someone who actually learned to be a baker, or would you let yourself be operated on by someone who actually trained as a butcher? Not sure, but that's happening in IT all over the place. Yeah? Underqualified people doing projects. Yeah? So the solution is really to fix the project team as well. Ensure that those who use the tool understand that tool. It's paramount to being successful in a project. Or to put it a little bit more pointedly, if you are managed by someone who only has business knowledge but no technical knowledge, then run. Okay, so main takeaway, when it comes to using database technology in IT projects, there can be quite a discrepancy between what should be done and what is done. How to cope with that. If you have to deal with database technology, be careful of the pitfalls. Most of the perceived database problems with web applications can be solved relatively easily. This includes most, if not all, performance problems. Yeah? Of course, sometimes it's hard to refactor things if the application code has too much issues, too much spaghetti, too much doing data processing stuff that should have been done in the database in the first place. Yeah, then it's over, yeah? But many of the problems can be solved. Be extra careful when it comes to security and privacy risk issues. Again, it's not an afterthought. You have to think about that from the get-go. And if in doubt, ask an expert and not a wannabe expert who uses shiny buzzwords. Yeah, that's it for this lecture. I hope you learned a lot. For the next iteration in summer, if you're interested, we're looking for tutors. And the criteria for us is you should achieve at least 1.7 in the final exam, have a talent for explaining technical content, and would like to join our team. Then you can apply directly to me, so you have to wait till the exam grade, for instance. The content of the lecture will not differ significantly, so it's more or less like we maybe renew 1 or 2 weeks of the content. Like this year, we introduced this project, the Django project. Tasks are then giving a tutorial every week, participate in weekly meetings with the tutor-in-chief, co-conception of exercises, and help with the exams, of course. Yeah, other than that, we also offer thesis if you're interested in bachelor and master thesis. So, okay, you should also have a 1 dot something ideally in your grade, because basically what we do in thesis work builds upon the stuff I teach here. So previously we had thesis work that you could also only do if you attended the core lecture. That's not needed anymore. So with a big data engineering lecture, you can do a bachelor and a master thesis, and then we can talk about topics. If you're interested, approach me. Topic-wise, we talk about topics briefly before you start. It doesn't make sense to talk about topics 2 or 3 months ahead of starting, because that's a dynamic set and other students come in, and we have new ideas, and so that's very lively how we do this topic stuff. Yeah, other than that, good luck on the exam. I hope you enjoyed it and learned a lot that will help you in your professional career. Important, if you end up working with databases somehow, feel free to drop me a line and tell me about your positive and negative experiences, in particular horror stories, of course, but also positive stories. So I'm really eager to learning more about that. So with that, and for the entire lecture team, thanks a lot. Good luck with the exam. And forgot, next week, there's like a summary and exam preparation session. My tutor-in-chief, Luca, will run the show. So that will help. He will summarize major takeaways from the lecture, maybe helps with the exam. Next week, same time.